Hello and welcome. In this video, we're going to just briefly look at partial derivatives. This is just a quick crash course to help us in what we need going forward. So partial derivatives are not derivatives that are only partially taken. That seems to be the case. But a partial derivative is one that we take involving a multivariable function. So we'll get into that in just a moment here. So we recall from algebra, we often see this notation y equals f of x. This is a two-dimensional problem, so if I just draw the first quadrant, then we are capable of plotting pairings of x against y. In the three-dimensional realm, here we're saying that z is a function of two inputs, x and y, and in order to be able to plot that, we would actually need a third axis, one that represents the x, one that represents the y, and then another that represents the z-axis. So in this in this three-dimensional region, here we have what's called the xy plane, and every single pairing of x and y will generate a unique value of z. So for instance, we might have, when x is 2, and when y is, say, 3, so that's going to correspond to this point right here, but that's just going to be the projection of the z value down onto that plane. So what we may actually have is this z value may have, let's say, a height of 3 units, and so this point will be offset 3 units off the floor. And in the situation where we have this, we may want to ask the question, well, how does z change if only x changes? Or how does z change if only y changes? As opposed to up here where we had some multivariable function, and here we said, okay, how does y change with respect to x at that point? And then we could find our derivative, and we find the slope of that tangent line. Same kind of idea applies here, but we have two directions we can go in. So if this point rests atop, let's say, some three-dimensional surface, like this is called a paraboloid, and we may want to say we're standing at that point, but how would the z value change if we went in the x direction or if we went in the y direction? So because there are multiple ways we could travel along this surface, not just left and right, but left and right and back and forth, we have two derivatives that are going to be associated with it. So let's say we have a function z equals 2x plus 3y. Z is going to be a total revenue measured in dollars generated by selling x pair of socks and y pair of, not globes, but gloves. And we want to know the rate at which z, the revenue, changes by when we increase x or we increase y. But here's the thing, we don't want to change both variables simultaneously, because then how are we going to know which variable caused the z value to change the most? How do we know whether x caused it to increase a lot, but the change in y caused z to decrease a little bit, and still in net it appeared that z increased? So here's an example. Imagine you have a garden 1 year, and in 1 year you get 10 pounds of tomatoes. So the next year, to get a bigger yield, you add fertilizer and extra water, and now you get 20 pounds of tomatoes. So the question is, did the fertilizer do it? Did the water do it? Well, in our minds you may say, of course it was the fertilizer and the water. But it's not that simple. That's not how things work. We have to scientifically investigate this. It could have been an interaction between that particular amount of fertilizer and that particular amount of water. It could have been the case that the fertilizer got you up to maybe 30 pounds, but then the extra water caused some of the tomatoes to be overwatered and they didn't produce as much as they could have, so it caused a decrease in 10 pounds of tomatoes, which is why you ended up with 20 and not 30. So we need to be very careful when we're analyzing things like this. So instead of writing, we're going to have two derivatives. How does z change when x changes? And how does z change when only y changes? So this is how we would write it in calculus. In multivariable calculus, we use this thing called the partial operator, and you could still say this is dz dx. The reason we use this operator, it's really just a historic reason. It's also a contextual reason, which is when you see this partial notation, that just emphasizes that the output variable is potentially a function of more than one input. So when you see the partial of z with respect to x, that should that should immediately tell you, oh, z depends obviously on more than one variable beyond x. That's all. This means the exact same thing though. And dz, dy. These mean the same thing, but are often used when there is more than one input variable. Hence the term partial derivative. So when we say partial derivative, it's not that we're not completing the derivative, it's just that we're focusing on the derivative with respect to only a partial set of the inputs. As in the tomato example, to see how z changes per unit change in x only, we treat y as if it were a constant. So back up here, we would have done better if the next year we had kept the same amount of water, but only changed the amount of fertilizer. And then if the only thing that was different from one year to the next was the amount of fertilizer, well then the 20 pounds were most likely attributable to the change in fertilizer. Or we could have said, let's keep the fertilizer constant and just add extra water next year, and then we could observe that any changes in the yield of the tomatoes would be due to the change in watering schedule. So back to our example here, z equals 2x plus 3y. To take the derivative of z equals 2x plus 3y. Well, first of all, one thing to note here intuitively is that every time you increase x by 1, so if x is 1, then 2 times 1 is 2. That means that 1 unit of socks contributed 2 units to your value of z. Well, that must mean that this 2 is in dollars per pair of socks, and that this 3 is dollars per pair of gloves, because this is kind of a linear function and makes sense. So to find dz dx, what that means is find the derivative with respect to x of 2x plus 3y. Okay, we're going to treat y as if it were a constant. So that means that if anything that involves a y, like here this 3y, this whole thing is just a constant. Why? Because we are going to treat y as if it were a constant. We're holding it constant. We're not allowing it to vary. So that means if we take the derivative of each of these two terms, and this whole thing is a constant, this is no different than, for example, taking the derivative of 2x plus 5. Well, the derivative of 2x will be 2. The derivative of 5 is 0. And this looks different. This looks like a variable quantity, but you just have to imagine in your mind that 3y is just some fixed number, and its derivative is going to be 0. So the derivative, or the answer to our problem, is dz dx equals 2. So how do we interpret that? Well, let's write our final answer as dz dx equals 2 over 1. So that means that this denominator is a change in x. X is measured in, I think we said that was going to be socks. So this is 1 pair of socks. And so that means if we increase the pair of socks by 1, then z will change by 2. Well, what does z represent? It represents the dollars of revenue. So you're going to get an increase of $2 of revenue for every additional pair of socks you sell. Similarly, if we want to take dz dy, now we're going to treat y as if it were a constant. Or, I'm sorry, x as if it were a constant. So in differentiating 2x plus 3y, we see that x is constant. Well, 2 times a constant is still a constant. So that right there is a constant. And therefore, the derivative of 2x will be 0. The derivative of 3y with respect to y will be 3. And so we'll get an answer of 3 over 1, which is dollars of revenue. But now we changed y, which was the pair of gloves, per 1 pair of gloves. So that's where we would want to use derivatives to see how does z change if you only change one quantity. Here are some examples. Let's just find all the partial derivatives of this. So here we're just using f. Remember, f and z are the same thing. This whole thing just represents z. Z is a function of these two inputs. So to find dz dx, we're going to take the derivative with respect to x of x squared plus y squared. So that means we're holding y constant. Therefore, if y is constant, the square of y is also constant. And therefore, the derivative of x squared with respect to x is 2x. The derivative of a constant is 0. And so we get 2x. In this case, the rate, how much z changes by for each unit of x depends on the current value of x. So we often then will need to plug in our point to figure out the slope at the point along that surface. So if this function, which it actually does represent a paraboloid, this three-dimensional function would look like this. We're not going to get into that here in this particular video, but it would look like this kind of shape. And so depending on where you are, you can see that the concavity changes. So if this is, I'll make this my x-axis, clearly the slope there is going to be different than the slope there, is going to be different than the slope there and there. So the value of x still is needed in order to know the rate of change of this function. And to find dz dy, we're going to take the derivative with respect to y of x squared plus y squared. And now we're just going to hold x constant. So any function of x is going to be constant. And the derivative of a constant is 0. The derivative of y squared with respect to y is 2y. So we get our answer of 2y. Now these are kind of the same, in a sense, but this function here is symmetric. So we'll leave it at that. I don't want to get too much into the interpretation of it at this moment. So now we want to find for this new function dz dx. So what are we going to do? Well, we're going to take the derivative with respect to x of 2xy minus x squared. Now things get more interesting here because we see that both terms involve an x. But if I do one thing here where first of all, we know that taking the derivative of terms means you take the derivative of the first and you take the derivative of the second. Here I'm going to make the argument that since y is being held constant, 2y times x, which is the same thing as 2 times x times y, we're going to make the argument here that this is constant, which means that if I take the derivative of 2xy, we know that we can factor constants out and just take the derivative of the function of x. So I'm going to take the derivative of 2xy, but I'm treating y as a constant. So it's like taking the derivative of 15x with respect to x. Well, what's the derivative of that? It's just going to be 15, right? Which is the same thing that you would get if you took 15, factored it out, and just took the derivative of x, which is 1. And so you get 15 times 1, which is 15. So now we need to complete the derivative of the second term. So I'm just kind of distributing this derivative operator in. So the derivative of x squared is, so the derivative of x is 1. So 2y times 1 is 2y, minus the derivative of x squared is 2x, and there's our final answer. And dz dy, similar process. We're going to take the derivative with respect to y of 2xy minus x squared. So I'll distribute the derivative operator. 2x is a constant, since we're holding x constant, and 2 times a constant is a constant. So the derivative with respect to y of y minus the derivative with respect to y of x squared. We could have distributed this derivative operator for our earlier example, but we just kind of did it in our heads. Now the reason I'm distributing this is because some of these terms, when they have mixtures of x and y, it's sometimes just a little bit easier to do it this way for your first try. So the derivative of y is 1. 2x times 1 is 2x. The derivative of x squared, well, remember, x is a constant, so the change in a constant when you change y is going to be 0. So this will just end up being 2x. So you can see we get different answers here for the two partial derivatives. And here's just another fun example, taking the derivative with respect to x of e to the x minus e to the y squared. The reason I chose this is because you look at this and you think it's going to be really complicated, but the derivative of e to the x with respect to x is e to the x, and we're finding dz dx here. We could also write df dx because that's the name of the function, so either notation will work. So that's e to the x. Now this is e is a constant, y is being held constant, the square of a constant is a constant raised to a constant power is a constant, so this whole thing right here is a constant. And so the derivative of a constant is 0, and so we end up with just e to the x. Now dz dy, will be the derivative with respect to y of e to the x minus e to the y squared. Similar reasoning leads us to the conclusion the derivative of e to the x is 0. And now we have to use the chain rule on this guy. So I know that the chain rule is going to take the derivative of the exponent. So the derivative of y squared with respect to y is 2y times the derivative of an exponential, which is just the exponential. And so my final answer is negative 2y e to the y squared. Now, this next example here, we have a chain rule problem because we see we have a product. We have a product of two terms. Both of them contain x and y's. So we're gonna apply the chain rule here. And what we know about the chain rule is that if you have the derivative of two things, it's the derivative of the first times the second plus the derivative of the second times the first. So if I want to find dz dx, I'm going to take the derivative with respect to x of this thing. So in order to do that, I'm going to, first of all, we've typically called them f and g. I'm going to call them, I'm not going to use f because we've used f here. I'll use g and h. So this is going to be g prime h plus h g prime. And so, or you could say g, that's the same thing, h prime g, excuse me. So the derivative of g, which is this guy, with respect to x, well, the derivative of x is 1. The derivative of y squared is 0. So that's g prime. H is just the negative y squared plus sine of x. The derivative of the h with respect to x is going to be, well, the derivative of negative y squared is 0. Derivative of sine of x is cosine x. And then multiply that by g, which is x plus y squared. Similar process for dz dy. Dz dy will still be this formula, but it will now be the derivative with respect to y. So the derivative of x plus y squared with respect to y is 0 plus 2y times the second, which is negative y squared plus sine of x, plus the derivative of the second with respect to y, so that's going to be negative 2y plus 0, times the first. There it is. So in Calculus 1, we learned that dy dx and y prime and f prime of x are all alternate notations. In multivariable calculus, dz dy and f sub y of x mean the same thing. Note that a prime symbol will not work since it is not clear which independent variable we are differentiating with respect to. So the reason we don't use primes and we use this subscript y, this means the same thing as dz dy, just like f prime of x would mean the same thing as dy dx. But we don't want to use a prime because, again, which variable are you taking the derivative with respect to? So it's just a new notation that helps us keep track of that. In the last piece of this video, let's also take a look at second derivatives of multivariable functions. So you can take the derivative of a derivative. You can take the derivative with respect to x of the derivative of z with respect to x. But the interesting part is that you can, if you have the derivative of f with respect to y, you could then take the derivative of that with respect to x. So you first take the derivative of your function with respect to y, and then whatever you get as that answer, if you take the derivative of that with respect to x, you get what's called a mixed partial derivative. We'll call this a mixed partial derivative. So you can see here that the first variable that this function was differentiated with respect to is y, and then the derivative with respect to x. So it's kind of a tricky notation to grasp at first, but I assure you it's not so bad because I'll show you a cool little fact in just a moment. But notice here we could also use the f sub notation. F sub yx, y is the first variable you took the derivative of with respect to, x is the second one. Or you could do the same thing but take the derivative with respect to x first and then take the derivative of that with respect to y. To show you how this works, to compute f sub yx, we first need to compute the partial derivative with respect to x of this guy. All right, so let's go ahead and do that first. Let's just say, okay, well, what is f sub y? Well, f sub y is going to be the derivative of this with respect to y. For the first term, 2x is a constant. The derivative of y is 1, so the derivative of that comes out to 2x. The derivative of x squared is 0, because that's constant with respect to y. Derivative of y squared is 2y. The derivative of minus 4y squared x, the negative 4x is a constant, so if I factor that out and just take the derivative of y squared, I'm going to get negative 8xy. Negative 8xy. The reason is because I'm taking the derivative with respect to y of y squared, which will give me a 2y, and then negative 4 times 2 is negative 8. Now if I take the derivative of that with respect to x, all right, well, the derivative of 2x is 2. The derivative of 2y with respect to x is 0. The derivative of negative 8xy with respect to x, so that means negative 8y is a constant. Factor that out, the derivative of x is 1, so we get minus 8y. Now, if I had first taken the derivative with respect to x of this whole thing, the derivative of 2xy would leave me with 2y. The derivative of x squared would be negative 2x. The derivative of y squared would be 0. And the derivative of negative 4y squared x would just be negative 4y squared. Now, take the derivative of that with respect to y. The derivative of 2y is 2. The derivative of negative 2x is 0. The derivative of negative 4y squared with respect to y is negative 8y. And the cool thing here is that these are the same. So we'll propose a theorem. It's not terribly difficult to prove this theorem, but we'll just leave it like this. The mixed partial derivatives are equal. That is, f sub yx is the same thing as first taking the derivative with respect to x and then y.